In this example, we're going to find the position, velocity, and acceleration of a car in a Scrambler ride. So this is the kind of ride at a theme park that has a car connected to a two-linked arm, where basically the car, which is this green box, is similar to the moon spinning around the Earth that's spinning around the sun. So if we're given this constant speed of each arm, L1 and L2, as well as those lengths, then we want to find position, velocity, and acceleration of the car at t equals 1 second. So first, let's put in some numbers here. So steps to solve this problem. The first step is to figure out the angle of each arm. So looking at these arms, this angle is theta 1, and then theta 2 is relative to theta 1. So say this is the x-axis. This is the y-axis. So now we can get vectors. So first step is use time and omega to get the thetas. Then use theta and L to get position. Then use position and omega to get velocity. And finally, take the derivative of velocity to get acceleration. So step 1, we'll find the angles. So we know that theta equals omega t. So theta 1 equals omega 1 t equals 10 times 1 equals 10 radians. Now, to get the angle that the car is with respect to the x-axis, we're going to have to end up adding these two angles together. Because looking at this, theta 2 is given relative to link 1. So if we want theta 2 relative to ground, we have to add theta 1. So let's go ahead and find that. Call it theta 1, 2. So then step 2 is to find the positions. So we'll need to get position of B first. RB equals RA plus RB with respect to A. Now, position of A is just 0 because that's where the origin is. So RB equals L1 cos theta 1 in the hi-hat plus L1 sine theta 1 in the j-hat. So that's position of B here. Now, if we want to get to the position of C, then we need to add position of C with respect to B to position of B. So now adding all of these together, then we get RC equals RB from above plus RC with respect to B, which equals negative 5.281 I hat minus 1.634 J hat meters. So next we need to get velocity. So for this, we'll first find velocity of b by taking the derivative of rb, and then we can find the velocity of c with respect to b. So let's see, velocity c equals velocity of a plus velocity of b with respect to a plus velocity of c with respect to b. Well, velocity of a is just 0, because a is not moving. So here we'll have velocity of b with respect to a is omega 1 cross with our b with respect to a, plus from velocity of c with respect to b, we have omega 2 cross with our c with respect to b. So now let's do those cross products. Omega is going to be in the z direction, pointing out of the page. So we'll have I, j, k, 0, 0, omega 1, which is 10. And then for RB with respect to A, that's the same as RB from over here. So then we'll add to that cross product the second one. In this case, we have omega 2, which is 18. And then RC with respect to B, which is here. Then we do these cross products. And then add those together. So now we have velocity of c. So then finally, we need to get the acceleration. So we'll use the relative acceleration formula. So for relative acceleration, we'll need acceleration of c equals acceleration of a plus acceleration of b with respect to a plus acceleration of c with respect to b. Well, acceleration of a is just 0 because a is not moving. But we still need the relative accelerations. So just because angular velocity is constant doesn't mean that acceleration will be 0 because the objects are moving in circles. And so we'll still have centripetal acceleration. So let's write out the formulas. Now here, because angular acceleration is 0, omega is constant, this is 0. And then this is 0. So we still have 2 additional cross products. Now this part, we have already found this is VB. And then this part is VC with respect to B. So we've already found these 2 pieces. So now we just need to put everything into the cross products. So for the first one, we'll have 0, 0, omega 1. And then VB from above, which is here. And then put in the second cross product with VC with respect to B, which is here, where we actually do these cross products out. And then finally add these together. So AC is 959.3 I hat plus 42 J hat meters per second squared. So now let's look at a simulation of this. All right, so this simulation runs for time going from 0 to 1 second. So we can see over here, t goes from 0 to 1 second in an increment of 1/100th of a second. And then I have put in the link lengths and the speeds. So it looks like here, the green car, negative 5.281, negative 1.634. So let's go back and do a reality check and see if that matches the answer that we figured out for RC. Negative 5.281, negative 1.634. So passes the reality check. Looks like the problem is correct.